All right, so this video is going to help you out with the Porosity Gizmo. What you should have open on your screen is the Google Doc on one side and then the Gizmo itself opened up on the other side. Before we get started on the actual Gizmo, let's go over some vocabulary words that are here on the Google Doc. The first one is, you say aquifer. Aquifer. It's a body of rock that can contain or transmit groundwater. Gravel is small, water-worn, or pounded down stones. You think of like a gravel driveway or gravel on playgrounds. Permeability is going to be a very important word for us in the next couple of days. Permeability is the quality of a substance that causes it to allow liquids to pass through it. So permeability simply means can water pass through that substance. Porosity, on the other hand, is a measure of the empty spaces within the material. So those two things, a lot of people get them confused. They think that they are the same, but they're not. Again, permeability is the ability of liquid to travel through the substance, whereas porosity is how many holes does it actually have. Are they related to each other? Absolutely, and we'll get into that. But they are separate, two different definitions that you need to keep straight in your head. The next one, sand. Like you already know sand. Saturated means to have complete moisture. Fully saturated means you are holding as much water as you possibly can. Sediment is any matter that settles to the bottom of a liquid. It could be something very small like silt. It could be something like sand or something that's, as large as gravel. Any of those are called sediment. Silt is super duper fine sand, clay, or other material. Silt is just maybe a word that we don't commonly use, but you think of how big sand is, and silt is just even smaller than that. And then the last word is surface water, water that collects on the surface of the ground. So pause the video right now, take a couple minutes to go do those prior knowledge questions. The questions relate to this scenario. Two students are given cubic boxes, meaning they are a box that's 10 centimeters by 10 centimeters by 10 centimeters, so relatively small. Robert puts a single glass marble that has a diameter of 10 centimeters in the box. Now that's a big marble, but like you have this box, one marble fits the entire box, whereas Susan puts 1,000 itty bitty teeny tiny marbles within her box. So the first question is asking you whose box has more empty space, meaning the space is in between the marbles. And the second one is whose box would be heavier. Again, do the best that you can, take a guess. It's just helping you think about the difference between permeability and porosity. So now we get into the Gizmo warm-up. It says some rocks and sediments have a lot of empty space in them. This allows liquids such as water or oil to pass through and be stored in them. Permeability, again, describes how easily liquids pass through a material, while porosity describes how much liquid can actually be stored. Remember, porosity is how many holes does that substance have, so water can be stored inside those holes. These properties are explored in the Porosity Gizmo. All right, so turn on macroscopic view. Good. Double check that we've clicked sand, gravel, and silt. Gravel consists mostly of rock fragments that are 2 millimeters in diameter. Millimeters are itty bitty, but let me show you what 2 millimeters would look like. 2 millimeters, you've got that big zero line. 2 millimeters would be like that big. Okay, so that's as big as a chunk of gravel. Sand consists of grains that are between 0.0625 and 2 millimeters in diameter. So sand is smaller than gravel. Silt, those grains range between like 3 thousandths of a millimeter to 0.0625. So silt is so tiny, itty bitty. So question number 1, which sediment do you think will allow water to pass through most easily? Imagine you had a cup of gravel, a cup of sand, and a cup of silt, and you poured water. Who's going to let water soak through the fastest? Just take a guess. Number 2, which sediment do you think could retain or hold the water the most? So once you've poured water in there, who's going to be able to hold the most water? Again, take your best guess. You can look at these pictures here to kind of help you. These are called the macroscopic view to help you with those answers. Now, question number 3 gets into a big idea for today. An aquifer is a rock layer that stores and allows the flow of groundwater. Compared to other types of rock layers, how permeable and how porous would an aquifer be? Remember, permeable is referring to the ability of a liquid to pass through it. Now, if an aquifer is supposed to hold groundwater, right? And then we can drill a well into it and take that water out. We would want more water to be coming in so we can keep taking water out. So we would want an aquifer to be very permeable. We would want lots of water to be able to come in. As far as how porous it would be, well, in order to hold on to water, in order to increase permeability, we're going to want more gaps in between those particles. So again, we'd probably want high porosity. We'll get more into that in the afternoon time. But let's go into activity A that says get the gizmo ready. If necessary, hit reset. The big question we're answering with activity A is how does permeability relate to the grain size of the sediment? So number one, observe. Above the gravel container, click on and observe water moving through the gravel. The first question says, does the water pass easily through the gravel or not? Well, considering the water just immediately fills up where the gravel is at, the answer should be yes there. Repeat the same procedure with sand and silt. So with sand, let's make a comparison. Notice that sand, it takes a little bit of time for that water to sink down to the bottom and then eventually fill back up, whereas gravel was pretty instant. And then remember, silt has even finer particles. So look at how slow it takes for silt to, for water to seep through to the bottom of that silt container. So those are your observations. Then let's go to, you can pause now, fill in your answers. Question 2 says gather some data. It says surface water pools on the tops of sediments. Surface water can indicate that sediments are saturated, meaning they are already full of water, they can't hold anymore, or that the sediment itself is not very permeable and isn't letting water in. So I'm going to click reset on all of these. And what we want to do is add just about 100 milliliters of water to each of those beakers. And just after I press stop, I want to record how much water is sitting on the surface of that. Is that what I'm doing? Record the approximate amount of surface water. Yeah. All right, so here we go. Are you ready? We're going to do gravel first. We're going to stop it just at 300, and you're going to take a look at how much surface water there is. 0 milliliters of surface water for gravel. So what does that tell us? That tells us that the water that we were adding went straight through the gravel and went straight to the bottom of that container. Let's do the same thing for sand. Press on. We're going to wait until just about 300. Remember, it's immediately after I press stop. Oops. So about 60 milliliters of surface water is on that container of sand. Now notice as time goes on, eventually that water is soaking into the sand. Okay, you got it. But what we care about is that water that was sitting on the top right after I pressed off, that is telling us that sand is less permeable than gravel. Let's do the same thing for silt. Get ready. And stop. So about 80 milliliters. So even more surface water compared to sand, especially more compared to gravel. What does that tell us about silt? It tells us that silt is the least permeable. The water that is sitting there because it can't very easily make its way to the bottom of that silt container. So question 3 says, analyze based on your data who's the most permeable, meaning who lets water in the most or the fastest. That would be gravel. Number 4, how do you know the surface water is not there because the sediment is saturated? Again, as time went on, what eventually happened to that water? That's what you'll think about and answer for question 4. So pause right here, fill in a couple of those blanks. Question number 5, draw conclusions. How is permeability related to the grain size of that sediment? The larger the grains that make up the sediment, the blank permeable it is. Let's think about it. Gravel had very large grain sizes. It let water go through right away, very fast, so it was more permeable. The smaller grain sizes that make up the sediment, the less permeable it is. Think about silt. Silt is made up of very, very fine particles. As soon as the water hit it, it took some time for it to actually let that water run through. Therefore, permeability blank as grain size increases, meaning permeability is also going to increase as grain size increases. The bigger the particle, the more likely water is just going to run through it. The very last question, suppose you were digging a well into saturated sediments. Why is the sediment's permeability an important factor in deciding where to put your well? Remember, the goal of a well is to draw water out. So if you have a well that you're digging and it's in silt, is it going to be very easy to draw that water out? Is it going to be very easy to let water back in? Not really. Water doesn't move very easily when the particles are that small. But if you're drilling a well in an area with maybe gravel and a little bit of sand, you'll probably see a lot of water output compared to silt, just because gravel is much more permeable. It lets water flow through it easier. All right, take a moment, make sure you have activity A filled out. I've already reset all of the containers for activity B, and the big question we're going to answer is, how does porosity relate to the grain size of the sediment? So now we're moving away from permeability real quick. We're going to talk about porosity. So first question, which sediment do you think can store the most water? Take a random guess, whatever you think, and also explain why you thought that for question number 1. Then let's go into collecting some data. It says release 400 milliliters of water into each sediment and wait until each sediment is fully saturated with water. So I'm gonna go ahead and click on, and click on. All right, it says record the amount of surface water in the first row of the table. So we're gonna let this run. I wanna make sure I'm doing this right. Yeah, we're good. We just gotta let it run for a little bit. Okay, so for gravel, notice that where the gravel is at is completely saturated. It can't hold any more water than what it's got. The amount of surface water that we have is 285 milliliters. So plug that in. For sand, again, looking, sand is completely saturated. We are left with 298 milliliters of surface water. And silt just finished up and it has 241 milliliters of water on its surface. All right, so part 3 says find the amount of water that is stored within each sediment by subtracting the surface water volume from the original water amount. Remember, we had added 400 milliliters of water. There's 285 milliliters that is sitting on the top. If we subtract those two, then we're able to figure out how much water is actually in that area with the gravel. So let me grab my calculator real quick. What you're going to do is take that 400 milliliters minus 285. Oops. It's helpful if you press all the buttons. And that leaves you with 115 milliliters. That means that there's 115 milliliters of water in this area with the gravel. Do the same thing for the other ones. 400 minus 298. There's 102 milliliters of water in that area with the sand. And 400 minus 241 tells us there's 159 milliliters sitting in with the silt. So just looking at those numbers, like who's able to hold on to the most water, looks like silt is able to hold on to the most. It has 159 milliliters compared to sand, who only has 102, and gravel, who has 115. But let's do one more calculation. We're going to calculate the porosity percentage by dividing the volume of water in the sediment by the sediment volume, and then multiply by 100. So we're going to take, for this first one for gravel, there was 115 milliliters of water in the gravel divided by 400, which was the total amount, times 100 gives us a percentage of about 28.8%. Then we'll do the next one, 102 divided by 400 gives us 25% porosity, and 159 divided by 400 gives us about 40%. So again, do those numbers kind of match up with what we were originally thinking? Yes. Silt is 40% porous, which means it can hold a little bit more water compared to like gravel, who's 28%, and sand, who's 25. So for question 5, who is the most porous? Who's the one who's able to hold the most water? That would be silt. The least would be sand. So drawing some conclusions, compare the porosity number to the grain size of the sediment. Does grain size determine the porosity of a sediment type? And explain why or why not. So this is kind of a trick question. I mean, look at your data. We know that silt is the most porous, which means it has all these itty bitty tiny little spaces between its particles in which it can hold water. It has so many of those little holes, those little spaces, holds a lot of water. It's got 40% porosity. But when we compare like gravel and sand, gravel is 28, like 29% porous, whereas sand is 25. Now that's weird to us in a way because you think, well, sand has these, itty bitty little holes, kind of like silt, but then gravel has these huge gapes, like gaping areas between all of its particles. But notice that like the numbers don't follow a trend, right? Just because grain size is increasing from silt to sand to gravel doesn't mean that porosity also increases. So be careful how you answer 6A. Definitely reference your data in that answer. And then 6B says, explain what you think controls a material's porosity. What makes one material more porous than another? And something that I want you to, hold on. Some things that you can consider for 6B. Think about the size of the spaces between the particles. Think about if those spaces are connected to each other. Think about, we'll just leave it at that. So again, think about the sizing of the spaces. Think about if they're connected to each other in order to answer 6B. All right, hopefully that helps you. We're definitely going to review a lot of this stuff in the afternoon time, so ask questions if you need to.